gems there.
Yeah. Yeah.
It's funny, because one person was like, it's so crowded in here. We went on Christmas Eve day, and the person next to her said, oh no, you can actually get up to the windows. Usually you can't even get close.
Wow.
So, no, he keeps it here.
Good morning.
That's why he asked you where. He thought he needed to do for this. It will come back up. That's what it is.
Well, Gary asked for one. At the end of the class. I got some for Gary in the folder.
Can't get through the day without my pain medication. It's just, luckily it's Aleve, not narcotics, but the Ollie people gave me a parking pass, which is nice, but walking from the parking lot L or construction, it's not good. I actually, next week, I think I'm gonna park across the street and pay.
So didn't Larry?
Larry did that yesterday. He got here, he's done it the last 2 weeks. The first time, there was 2 slots.
Yeah.
Yes, the last time was 1. Yesterday, there were none. So he had to park over by the law school.
Yeah,
and
it
walk.
just,
Well, they used to have a parking lot right in
Yes.
front of this
Right.
building,
It's
which you
the
could get if
construction
you had a
workers.
handicap.
right, I know, there's a sign out on Evans, public parking, make a right turn as you're approaching this building, but no, you can't.
Right.
It's,
The problem is the construction workers.
yeah, there
All
seems to be a
parking
little
that lot.
construction here.
Yeah.
It's a lot.
It's, I was just in Dubai. While you were in Washington, I was in
Right.
the Middle East, and unbelievable. Construction towers everywhere. Just,
But that hasn't changed in over a decade. I was there a decade ago,
Right.
and same thing.
right. Well, yes, they, out of a pile of sand 50 years ago, they now have a spectacular city.
Yeah. And as far as we should do this, there's a class in seminar room right outside where the filters are.
Oh, yeah.
And you have to walk through, get it, and it has a-
There's a reason I'm showing lecture 2, because I want to do a quick summary.
Maybe six.
I missed last week,
Why me go through one?
and it's possible some people have not had a chance to look at the video I created. So I think because there is a connection between this and today's topic. So we'll run this like an airline, we never leave early.
Or do you leave on time?
Yeah, we try to leave on time, but we never leave early. We don't want to leave somebody behind. While we're waiting, any questions that people have things you want to talk about?
I'll make quick announcements. Silence cell phones and lids on drinks. And that's all I got.
We're trying to do a better job on the videos. So I've moved the camera much closer to me. Remember last time it was back where John is, and it's here. Welcome. Because getting the sound to be adequate on the video is a challenge.
I thought lecture 2 videos were pretty good.
Those were because of my illness. I
Yeah.
did a fill-in I sat in my little office at home, and the microphone was right in front.
But the links on your videos are not clickable. And they're not even copyable.
Oh, on the video, right.
Yes.
You have to go to the presentation material.
Where
Those,
is that?
the view graphs are, I provided a link,
You did.
Yes, sir.
The first email, right?
very first email where I introduced myself to the class. There's a link to my, as I finish these lecture notes, I put them as PDFs in a folder that you have access to.
Okay.
Yeah, there were
I'll have
two
to-
emails.
I'll see you afterwards.
Yeah, there were
or
two emails.
Talk to me at the break.
Yeah, and one was, here's the video, and the other was, I've invited you to join a group. And I think that's the one you're referring to.
Right.
Which has all the links in it.
Yeah, I didn't understand that.
Yeah.
We'll talk about that. So, I think we've got everybody who's on time. A couple of pieces of news from the world of astronomy and astrophysics. Yesterday, an audit group put out a report about the James Webb Space Telescope, which is the next big thing. Does not replace Hubble, but it's a powerful, powerful machine that we'll cover in one of the lectures in detail. And they announced that the launch date of, I think, March of 2021, which is 7 years late already, the chance that NASA will launch on that date is 12%. So that's kind of a problem. And the new budgets are being considered right now. I saw at least one headline just this morning that the staffers who are on Capitol Hill, who are talking to NASA executives, are saying, we're going to ask you to stop working on James Webb Space Telescope until we have a reasonable budget and a realistic launch date. So that's a real problem. The other thing is today the 30th? Today the Spitzer infrared telescope is being retired. I brought a short presentation on that topic. If we have time, I'll show it at the end of today's session. This is a telescope whose genesis was in the mid-1970s, an infrared telescope that can see deep into galaxies and see things that a visible wavelength telescopes cannot see. So that's something, if we don't do it today, we'll do it in a future meeting. But the telescope is being retired because it has a limited supply of cryogenic or low temperature fluid to keep the telescope and the sensors cold. Hello. And so Spitzer has come to the end of its useful life. And 16 years of data. So let's do a question.
There is a wonderful picture on the front page of the New York Times today of the surface of the sun.
Oh, yes. Highest resolution picture ever taken of the surface of the sun, and it looks like yellow cottage cheese to me.
Yeah, or popcorn.
Or, yeah, yellow. There it is.
Yeah. Great.
Ansel comes prepared. Yeah, take a look at that. This is,
Each one of the kernels is approximately the size of Texas
right.
in this picture.
Let's see, a question back here?
I was curious about the requirement for cold on the, it seems like it'd be fairly cold up there anyway.
Okay, so just to make sure the audio comes through, I'm going to repeat the question. So the question is, why would the Spitzer telescope have to be cold? And the reason is it's looking at infrared radiation. So indeed, you're right. Telescopes out in space, particularly if one's not looking at the sun, which is almost all of them are not looking at the sun, they get cold, but we got to give them an extra boost so that the noise in the sensor is at absolute minimum. So if we go through the lecture notes on Spitzer, I'll show you how they do that. It was done actually in Boulder, Colorado at the place I used to work. Ball Aerospace invented the cryogenic storage system. But this is a big deal both for ground and space-based telescopes. To get the camera has to be cold. That reduces the noise. And the telescope itself, which is based on mirrors, the mirrors have to be super cold. Otherwise, the glow from the telescope mirrors obscures the astronomical objects.
Would it be close to absolute zero out there?
It is, the telescope, the spacecraft and telescope without cryogenic fluid will not get that close to absolute zero. It would get down at like 100 Kelvin, 0 Kelvin being absolute zero. So it get to like 100 Kelvin just sitting there naturally. So you have to have either a mechanical system, a refrigerator, or a store of gas or fluid to keep it cold. And that's one of the big challenges they faced building the Spitzer telescope, which we can go into. The history is very interesting. The technical challenge of making that work took 20 years to work it out. So let's do a quick, let me see if this works. Yes. So I don't want to make you dizzy, but I thought I'd step through lecture 2 and make sure we're all solid. Hello, welcome. We're just getting started. I want to make sure we're all solid on the concepts that are important in the early universe. We need, do we have room back in the back there?
Yeah, there's the room back here.
So one of the key things is shown here. It's a little obscured by the label, the titles, but what this is a periodic table of elements that you all experienced in high school chemistry, but it's color-coded here at the top. So you see here blue. Any one of these elements that has a blue, like helium and hydrogen, helium, and a little bit of lithium, that's the result of those elements being created in the Big Bang. And when I say what we're looking at is the fraction of, for each element, where it came from when we look at the census of lithium in the universe, which astronomers do all the time. They look at galaxies, and using spectroscopy, they can estimate the amount of lithium in a particular galaxy. So if we look at all the lithium in the universe, this one here, we see that maybe 20% came from the Big Bang, and most of it came from the dying of low-mass stars. And so this is color-coded in that way. When we had our first session, I mentioned the Hubble Deep Field, a photograph taken over hundreds of, actually, yes, hundreds of hours, 2 million seconds of exposures whenever they had time between assignments for the Hubble telescope. They would point at this spot on the sky, which is that where that little blue square is relative, that's how it compares to the size of the moon. So they picked a spot that appears empty, and they just kept taking exposures and accumulated 2 million seconds of exposures. I actually went on a bike excursion 5 years ago with a friend of mine organized, and the guy who designed this was one of our members, Bob Williams, who ran the Telescope Institute, which is a facility on the campus of Johns Hopkins University in Baltimore. And Bob was the director, and the director gets allocation of Hubble telescope time. And he said, let's look at something where there's nothing there, but there is stuff there. These are the oldest galaxies we've ever seen. And morphologically, structurally, they're very different than the ones that are more modern. You have a question?
Yeah, you know, when it says 2 million seconds of exposure time, it just seems like an impossible job to keep it focused on that point. You know, the Earth is moving around the sun at about 70,000 miles an hour, and the telescope is going around the Earth at 20,000. How do you keep it focused?
Well, the focus is not the issue, because astronomical telescopes focus at infinity.
Right.
For those camera folks, that's
but pointed in the right direction.
pointed. the technology in the Hubble Space Telescope for pointing is extraordinary. And so what Steve is talking about is, Earth is going around the sun is moving, the galaxy is moving, that's a small effect. But the telescope is going around Earth that whole time. So if you want to take a picture of, let's say, that spot up there, you can do it when the telescope is here, and you can keep doing it, and that's sort of like 40 minutes of exposure per orbit. And then the telescope is obscured by Earth. So the software they use at the Telescope Institute immediately reorients the telescope to look at other objects because they cannot see that spot because Earth is in the way. And then when they emerge, they can start looking again. And that's what they did. And the pointing control is, it's like, I'll make something up that's about right, that they can, with 90% accuracy, point to a quarter, a metal coin, on the Empire State Building from Los Angeles. It's just amazing stuff. So we have some recommendations for books and so forth. If you haven't looked at this, you can look at these charts are in the folder where I'm storing all the lecture notes. These are pictures I took, not this one, but these I took during the eclipse. So let's skip ahead. This is the central idea that a big bang, something happened here. We have this interval of 400,000 years roughly, during which atoms could not form. Even the components of atoms could not form. The temperatures were so high and so destructive. And then things cooled down. We'll cover this in today's lecture in even more detail. And then for a long time it was total darkness. Because there were atoms, but there weren't any stars. So we had total darkness for 400 million years. So we have 400,000 years before the universe was cool enough to allow atoms, and then you have darkness for 400 million years. And then we're into this interval where we start seeing individual stars and primitive galaxies. Yes, sir?
We had total darkness, how do we know there were atoms?
Because we eventually got stars. There's nothing to see. It's just like the police shooing people away. There's nothing to see here. There's nothing to see in this dark interval. But suddenly stars start appearing, and then galaxies. We're not able to take pictures of individual stars from that era. An individual star, now remembering the universe has expanded, those stars are very far away, but galaxies are bright enough we can see them. This is a similar picture, and this shows how far back various instruments, including ground-based telescopes and Hubble. Here's the oldest thing that Hubble could see. We're looking back to just sort of like 500 million years after the Big Bang. We start being able to take pictures. Yes?
Did you tell us how stars became galaxies?
Gravity. Gravity is the weakest force in the universe that we know about. We understand lots of stuff. Oh, and accidentally, here it is. So we have four forces. We have the strong force that holds all the protons together inside of atoms, and it's extremely well understood. We can make all sorts of predictions. This is how we know we understand it. We can predict the behavior of various kinds of atoms and what happens if you shoot neutrons at them and all that stuff. That's the standard model of particle physics, and it's extremely well understood. And so the strong force, which I liken to Scotch tape, there's no force between protons and neutrons until they touch, and then you can't get them apart. That's the strong force. The weak force that's mentioned here, this little branch here, the weak force mediates radioactive decay. That's extremely well understood. Electromagnetism, how we run our society and shock our dog when we rub our feet on the carpet, that's extremely well understood. And then there's gravity. And you can see here, these are essentially grouped in strength. And gravity's way down there. Gravity is the weakest force that we know about, but if you give gravity time, it will take this star and bring them together. If you take an empty universe and put two stars out there and just let them go, they will collide, or at least go into orbit around one another. Yes?
So that, maybe it's related to my question of why are the illustrations cone-shaped? Why is the universe cone-shaped?
Okay, so good question. So this is what you're talking about.
Yeah.
So this attempts this is a graphic attempt to illustrate what is called inflation. That is the immediate rapid expansion of the universe in the first tiny fraction of a second, followed by a more gradual expansion. So we have this explosive increase in size, and then along here we have increase propelled by dark energy. But that initial increase was so huge that it explains a lot of stuff, which is in the video for lecture 2. So let's try to get through this because there's so much to cover. There's that same picture, it's more details. This is important. This is the success of Big Bang nucleosynthesis. That is, so I abbreviated BBN through the rest of all the lectures. The idea that we know the composition of the universe, what are the abundances of different elements, maybe a little hard to read, but this over here, that's hydrogen, and way over here we have thorium. And this is the abundance in the universe of all the different elements. This is all explainable with the modern theory of Big Bang nucleosynthesis, stimulated by this guy, Gamow, who has a building named for him at the University of Colorado. We'll talk about this more. This is what happened in the first, roughly the first hour of the universe when Big Bang nucleosynthesis created a large fraction of the universe, hydrogen and helium. And there's some complexity here. There's some problem explaining lithium. We'll talk about, there's the periodic table again. There's some background on subatomic particles. We don't need that for today's conversation. This is kind of a joke from this book, which I recommend, called We Have No Idea, explaining cosmology and astronomy and say, yeah, we understand some stuff, but there are a lot of unanswered questions. And this is the simple, I say that in quotes, simple interaction between the forces and particles in the early universe. This is technically correct, but it's kind of comical how complicated it is. Inflation is what Gary was talking about, is why do we have that drawing doesn't just look like the horn of a trumpet. It has a different structure to it. It's because of the theory of inflation, which we will talk about. There's some information here about our trajectory through the universe, the so-called light cones, and the cosmic microwave background, which is what we'll talk about today. So, given that, let's go to today's topic. Questions? Yes, sir.
Yeah, in the charts for last week, which you just ran through quickly, you had that, you said that the temperature on the right and the left were really very close to being the same.
Right.
How could that be? And I didn't understand why, since we know that space is curved, light going through space, you can see a star behind another object, you see two images of the star.
Mm-hmm.
You know, why couldn't the right and the left be looking at the same thing?
Well, there is one possibility. I'll start with the least likely, but it is a possibility that when we look at the universe, that the universe is a lot smaller than currently considered, because we're looking at objects where the light has propagated through the universe multiple times. So we look at a spot on the sky, we see a galaxy, And we have no way to know that something nearby is actually